This is EE597 with Professor Krishnamachari on Wednesday, July 20th, 2016.
Okay, so let's resume with our discussion about the network layer. Can I have the overhead camera, please? So the last class, we started to think about what the network might look like from a layer 3 or routing perspective. So you have a set of nodes, and we want to, for some reason, create a multi-hop wireless network that is routing the data between them, and you get a certain set of links that are active. And we said that one way to kind of characterize the quality of each link at the link layer is called the packet reception rate. That we typically look at as just going from 0 to 100%. And one comment we made that in typical deployments, what you actually observe if you were to plot packet reception rate for a link as a function of the distance between the transmitter and receiver. So if I take the transmitter, here's my receiver, and here's the distance d, and I want to characterize what that packet reception rate looks like as I vary this distance d. What we said is that although maybe in an ideal environment you might expect it to look something like this, like it's 100% up to some range, and outside it's 0, so this would be like an ideal, sometimes called a fixed radius model. But really, if you observe empirically what it ends up looking like, we really see distinctly 3 different regions. The first region, that link is indeed close to 100%, and we call this the connected region. And there is indeed a distance after which it's 0. But if you kind of look at the link for a significant distance between the point where the link was perfect and the point after which the link virtually you don't see any packets, there really is a region in between, sometimes called, so this is called the disconnected region. So there's typically a region in between called the transitional region, in which this packet reception rate is somewhat more stochastic, and actually you will sort of see it all over the map. And intuitively, it may be true that sort of the average values are behaving a certain way, so there may actually be a certain mean or expected value of the PRR as a function of distance, but really for any given link at any given moment in time, it's not going to give you the mean value. It might most likely give you the instantaneous PRR, which is sort of random. And not only is it random, if you actually measure the distribution of this, the random distribution of PRR, so typical distribution of PRR at a given distance in the transitional region is bimodal. And what I mean by that is if you kind of go back to plotting PRR as a function of SNR, let's say in the dB scale, if the signal to noise ratio is really low, you get almost no packets being received, and beyond some point you get packets are received. This range of SNR values in which the PRR goes from being 0 to close to 100% tends to be pretty narrow, right? Typically 3 to 4 dB. And because this range is quite narrow, it means that unless your received signal strength to noise ratio fell in that small window, you're either going to see, very good link or very bad link. It's very rare that you see sort of like mediocre quality links in the middle. So for that instantaneous, this is sort of instantaneous PRR, okay? Instantaneous. So if I kind of look at this scattering of PRR values in the middle, actually what you'll find is that a lot of them are like down here or up here. Very few of them are sort of in between. And, at the lower distances, more of them are on top. At the farther distances, sort of more of them are scattered at the bottom. So let me actually show you what this looks like. With a paper. If I could get the screen behind me, please. Okay. So I'll post this paper on our website. But it was a study that a former PhD student who worked with me here at USC did, where he characterized what the link quality looked like at different distances for low-power wireless embedded modes, which are some of the radios you use for sensor networks and low-power IoT. So here is the curve I just kind of drew, right? This is the packet reception rate as a function of SNR. Let me make this bigger screen. So this figure kind of shows what I was just talking about. So there's about 2 or 3 dB range over which that packet reception rate goes from being very low to very high. So this curve is actually plotted for the particular radio based on the specs of the radio, depending on what kind of modulation scheme it's using, how many bytes are in each packet. So all of those are taken into account in plotting this curve. If you actually look at the typical signal to noise ratio as a function of distance, we talked about this earlier in the class as the radio propagation model. It has a mean path loss. This is the simple path loss model, which sort of says that things are going to decay with distance, as like 1 over distance to some path loss exponent. But there's going to be some stochastic variation around that mean path loss. That's the log normal distribution we typically use to model it. So if you actually take measurements, and these dots come from real measurements, this is what you would observe. So if you look at this small range of values where below this you get almost no packet reception, above it you get almost perfect packet reception, that's plotted on this second plot over here as these 2 bars. So this is the high end of the SNR, this is the low end of the SNR. Any SNR that's above this range results in 100% packet reception rate, or close to. Any SNR below this results in virtually no packets being received. So it's only this region in the middle, but because of the nature of this fading, this distance is quite large, where the packet reception rate sort of goes on either side of these thresholds. But you can also start to see why it might be bimodal in that most of the points sort of lie on either above or below. So with some random probability, it's very high quality link or a very low quality link. And so if you were to model what is the result of this, you end up with that transitional region. And if you were to actually look at what the let me see if we have any examples of the PDFs in this paper. I think everything here is a CDF. Okay, so let's just use the CDFs at least to give this idea. So if you look at these, let me find a better curve. So maybe this curve over here. So this curve shows the CDF of the packet reception rate, typical values for each of the three regions. So if you're in the connected region, the CDF looks something like this lower curve. It says that the probability of having a packet reception rate less than 0.8 or 0.9 is very low. It's only about like 0.1. So this curve is very skewed, kind of being very low and then really peaks up at 1. So it says the majority of your links are 100%. Okay, that's what this curve says. At the other extreme, the disconnected region, more than 85-90% of your links in the disconnected region have zero PRR. None of the packets are going to come through. Right? So there's very little packets coming through as you, or the packet reception rate of higher values have lower and lower probability. In the transitional region, what you're seeing is not sort of this, let's say, a straight line going from the 0 to 1, which would imply like a uniform distribution. If all of those PRR values had equal ranges, then the CDF would be the integral of that PDF, and it would show something that looks maybe uniform. But in fact, what you see is something that has this sort of sinusoidal shape, which means that, for example, you know, about 30-some% of the links have, in the transitional region, have very poor quality, close to 0. More than about 25, you know, depending on where you want to draw this line, about 25 or 30% of them have very high quality links. And sort of in between, there's about 30% of the links in this picture shown have a PRR between 0.9 and 0.1. So sort of it's bimodal in that sense. Okay. So if you were to in fact, this is real measurements from so this figure at the bottom, I think, is a real measurement of what that link quality looks like. The PRR is a function of different distances. So these are just, you take two of these wireless devices, place them at different distances, at different locations, and take these measurements. So you do see, you know, the connected region very clearly, most of the packets get through. Disconnected region, clearly, most of the packets get through. In the transitional region, there's this stochastic variation, but you'll see there's a lot of points clustered near the top at this end, and a lot of points clustered near the bottom at this end. And there's only about 30% of the points in this region are in the middle. That's sort of the point we're trying to make. Okay. So if I can get back to the overhead camera here, please. So if you want to kind of imagine what that's describing, so if this was sort of PRR, and you're looking at some, you know, typical, let me draw maybe the PDF in the transitional region. So you might see a curve that looks something like maybe, right, something like this, where this point here is 100%, this point here is 0%. So you're seeing like a lot of links with low quality, a lot of links with high quality, and maybe relatively smaller number of links like right in the middle. And this dip is because of the fact that that range over which you would get intermediate PRR values is not very large. Okay, so that's sort of the intuition. So sometimes this is what motivates our outage models and the Gilbert-Elliott model that we studied before. So you can think of these links in the intermediate region sort of switching between being in a good state and a bad state. So sort of a discretized version, right, of this picture would look as follows. It would say there is a sort of, if I break this up into little bins, you know, I can kind of turn this into a picture that maybe looks something like that, where there's a certain percentage of time the link is bad a certain percentage of time. Right? So think of this as the bad state. Think of this as the good state. I can have like a two-state model that describes my channel. This is kind of where that's coming from. Okay. So if you're in the connected region, the probability of being in the good state is close to 1. You're always there. In the disconnected region, it's close to 0. In between that probability of this Bernoulli, two-state random, for now let's talk about it as a random variable, that probability is decaying from 1 to 0. Okay, so that's sort of a different way to interpret this curve over here, right? So we can basically model the probability that link is in good state as being close to 1 up to a certain distance, 0 after a certain distance, and then this curve that's kind of decaying below that. So I can think of each point here. So this is sort of an idealized two-state model. Okay. So from that packet reception rate, we've kind of abstracted away the possibility of intermediate values, and we're just saying it's either good or it's bad. And if it is good, then here's the probability with which it's good, and that probability is close to 1 in the connected region. It's close to 0 in the disconnected region. And in between, there's some process by which it's decaying. Okay. So this gives you like a way to model link quality spatially as well. This doesn't address how that should vary temporally. So for temporal variation, may be modeled via a Markov model. Okay, we talked about this earlier in the course. So you can actually take a link, and when we talked about good states and bad states, so the link, this way of thinking about it, you can think of the good state as basically the packet reception rate and being close to 100%, and the 0 state as being the packet reception rate is close to 0%. So this kind of justifies, if you will, a little bit the empirical observation I showed you, that really since only 30% of the time is it somewhere in between, maybe we can kind of focus on the most common cases of links being either pretty good and pretty bad as two different states, and just kind of thinking about our network in that way of doing it. But more generally, you can also just talk about the probability of being in a good state as one way of capturing the quality of the link. So that's what I wanted to say about kind of how do we abstract the network. So if you want to kind of imagine now, one way to model a wireless network, so you have a set of nodes, you might know the distances for these nodes. You could assign a probability to each link as a function of the distance of that link, that link would be good. Okay? So for example, if you want to model this as an IID network, then basically that probability each time you either make the link good or bad with that probability. Right? Or if you want to use a Markov chain, then each link here is associated with the two-state Markov chain where the link qualities are transitioning based on the probability of going from 0 to 1 or 1 to 0. And those probabilities basically capture the coherence time of each of those links. And if you have environments in which there's a lot of mobility, there's a lot of dynamics, these link values, whether they're good or bad, are going to change more frequently than if it is a system that is in a remote area. Then if it's bad, it tends to kind of stay bad. And if it's good, it kind of tends to stay good. But you can think of that from a Markov model perspective as having a very long time constant. We talked about the coherence time and how we can derive that for a Markov chain. So we can kind of model this system this way. So for example, from the perspective of generating, let's say, realistic simulations of a multi-hop wireless network, if we can characterize this curve that shows how the probability would vary with the function of distance, you can then generate random link qualities as a function of time, whether you're using a Markovian model or a simple IID model. You can sort of generate instances of the link quality for a multi-hop network just by knowing sort of where the nodes are located and computing pairwise distances and then observing them. Okay. Okay. So this is really more of a modeling issue. It's like if I had to create a simulation, what would be a reasonable way to generate that simulation so that it might match what I observe? Okay. And the key thing to realize is that this way of modeling it is more sophisticated than the simple fixed radius model. So in a fixed radius model, it just says either there is a link or there is not a link. Right? So in fact, in this picture, there's some links I didn't draw. And this is kind of implying that the link quality is 0. There's no way for them to send messages to each other, which may be true if they're in the disconnected region. But in the ideal model, the presumption is that every link that's there is perfect. But that's not true in a real wireless network. Okay. Just to reinforce this point a little further, I think I've shown this before here, but let me show again if I can switch to the screen again, please. So these are the packet reception rates measured on the TutorNet testbed at USC on 2 different channels. These are frequency channels that 15.4 radios run on. And the plots here show, and the student used PDR, packet delivery ratio, instead of packet reception ratio, but it's the same thing, shows either no link at all if the packet reception rate is less than 30%, or shows a red link if the packet reception rate is between 30 to 90%, or a green link if it is very good quality, right? So the figure on the right, this channel 26, the figure that's on the right, which has a lot of green links, happens to be a radio channel that has no external interference. So on that on that simulation, the reason that the links are green most of the time is that the links that are bad are so bad that they won't even be red. They're sort of a very low quality. Okay? So you're not seeing a lot of intermediate quality links. Those red links are not showing up so much in that right figure. There are some links that are really bad. They just don't show up at all because they don't even get 30% of the packets. Right? The figure on the left, however, does show intermediate quality links. And a lot of them, these red, are actually red if you look at on the left side of that. But this is not because of fading effects. This is because of external interference. So in fact, we just said that a bimodal distribution or a good state, bad state model is a good model for a wireless network. That's in fact only true if we ignore external interference. So if you're operating your network in an environment where there's a different network that's operating and affecting the quality of your links, then it's just not a pure function of the fading effects that influence what the quality of the links is. There's also a lot of on-off interference coming from the other sources. And so, for example, if you're in in this case, this is the 4th floor of the RTH building. It's an office environment, lots of student labs and faculty offices. And so what's happening is that when people are using the Wi-Fi access points, they are burstily being occupied on the channel a certain percentage of the time. And whenever they are on that same channel that's interfering with 15.4 radios that we're using, because 802.11 and 15.4 happen to share spectrums. In fact, we can even show that. Maybe there's a, if not a YouTube, maybe I just want to look at this in Google. So here's a typical figure that shows this. So channel 18, which we were looking at on the test bed. Okay. So channel 18, which we were showing on the test bed over here, is overlapping with channel 6 of your 802.11 access points. And that's a very commonly used channel in a lot of access points. So if that channel on Wi-Fi was being used 40% of the time, all of the links that were perfect or close to perfect due to the link quality and fading effects are going to deteriorate to 70% link quality. Because 30% of the time when they're operating, they're going to suffer interference. Right? And so that interference in this case, because 802.11 has much higher power than 15.4, anytime it's on, you basically knock out the link. So those red links that were showing up on the 18 were really because of the interference. So the comments I was making before are really assuming there is no external interference. If there's external interference, then we want to maybe even modify our way of thinking about it a little further. So it's not just a good state, bad state, but you're also having another background process which affects the probabilities further in terms of the link quality. Okay. So if I can get back to the document camera, please. So where we are with all this is last time we talked about a metric called ETX. And this was really itself an alternative to blacklisting, which basically means avoid using links with low PRR, less than theta for some threshold. ETX is a metric for use in routing, and if you want the simplest possible implementation of an end-to-end routing mechanism on a static multi-hop network, so the sort of simplest mechanism would be use either link state or distance vector routing to compute shortest paths from end to end using ETX as the metric. Okay. This produces paths that are minimum in terms of the sum of ETX. So if you take a particular network, it might compute a path for you, that goes through the network, follows a particular set of nodes as intermediate hops, which has the property that if I measure the ETX on this link, 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 the sum of those values is as small as is possible for any path you could have computed from the source to the destination. And typically, it will not pick very short number of hops, because short hops, for example, from here to here to here, might involve these long distance links which have very poor packet reception rate and therefore a high ETX. Nor will it necessarily route through every node in your network, because of course, eventually if you keep adding more and more edges, the number of terms will also start to grow, and that will also contribute to a bad ETX total. So it'll sort of pick an optimum route that takes this into account. So I want to talk about two innovations in routing. And the first innovation is the use of something called anypath routing. Sometimes also called opportunistic routing. And the second innovation is the use of something called back pressure. And what these two innovations do is, in some sense, they try to address different aspects of how one might improve over the shortest ETX routing. So there's nothing wrong with this approach. It's pretty robust. It in fact works. And quite frankly, if you had a system deployment to do in a few short weeks, you don't want to reinvent the routing protocol. You want to grab a routing protocol off the shelf, and you want to just make sure that it's using a good metric. And that's what this approach is really doing. But if you really want to think deeper about system design and try to squeeze out more performance out of it, you might look for where can I get more performance out of my system. So the first is to recognize that because it's a wireless network, there's one thing that's different between wireless and wired networks, which is that when this node sends a packet to this node, in most wireless networks, there are exceptions, the links are not directional, they're actually omnidirectional. We did look at the NetBlazer community broadband network, which was directional, but for example, TutorNet and a lot of wireless sensor networks and IoT networks are not directional typically. So if you have a network that is not directional, that same message when you're trying to send to this node is also being sent to other nodes. In fact, it might accidentally even reach this node when you're trying to communicate with this node, and this node didn't hear it, but this node already heard it, right? So by enforcing a particular path that every packet must take, what you're basically saying is if this node happens to accidentally hear the message that was sent here, it should ignore that and wait for the message to be routed to it through the intermediate hop. But you can see that it's somehow inefficient. If there was some way that you could have directly picked that message and run with it, that would have helped your system. And so this first innovation really addresses, can we improve it in that dimension? Can we when opportunistically data is delivered because of the broadcast medium to nodes, can we somehow adapt how the data has to be routed so that we don't have to take the hard set path? Okay. So another way of thinking about it is it's sort of trying to create more diversity in the routing, and because it's a broadcast medium, the messages are being heard at multiple locations. Can we exploit that diversity to improve the efficiency? So that's really sort of, the first one is really a diversity oriented innovation. And the hope is that you can improve the reliability or the efficiency of your routing by exploiting the broadcast advantage. The second approach is really a technique that says, if everybody follows the shortest path through the network, what might happen is that all of these routes, because they're being independently computed for every pair of nodes, might end up traversing the same region of the network, for example. And what that might do when you have a heavily loaded network is it might increase the queues on those nodes in the network, and they may increase the queues so much that this starts to increase latency because of queuing. So when you're doing routing at the network layer and you just focus on link costs, you don't care about optimizing multiple routes together in order to improve, say, queuing latency. And so back pressure routing is an approach that focuses on more taking into account what the queue state is into deciding how packets should travel. And this is sometimes referred to as queue-aware routing. And both of these innovations kind of make routing a little bit more dynamic than identifying a fixed set of routes for a pair of source and destination nodes in the network that we don't change at all. In the first case, the route might change because different nodes might get the packet sooner or later. In the second case, the route might change because certain sections of the network might be getting congested and their queue starts to go. So in either case, you sort of modify what route packets can take dynamically. And so both can broadly be thought of as sort of dynamic routing schemes. So that first dynamic routing scheme is called, as I said, anypath routing. And there's a very classic paper about it going back to not very long ago, about 2008 or so. And that's a paper, again, that we'll post and have you take a look at. If we can please project the computer over here. So here's the paper, and it's from 2008. Professor Kleinrock, I forget if he's retired now, but for many, many years has been at the CS department at UCLA, and he's considered one of the founding figures for networking. In fact, he was there at UCLA when they deployed one of the very first router nodes on the internet, back in the 70s. He's credited with a lot of basic results in queuing theory and so on. And his PhD student, one of his last PhD students, in fact, Raphael Laufer, wrote this paper a few years ago showing how we can exploit the broadcast advantage in wireless networks to improve the quality of routing. And I have sort of a personal connection to the researcher because he invited me to be on his thesis committee, so I got to actually hear him propose and defend his thesis on this topic. But the key idea that he had can be kind of explained with an illustration, and here's sort of the illustration from their paper, and we can just use that to understand what they're doing. So let's look at this simple topology. You have a node I over here that wants to get a message to this node over here. And there's sort of three intermediate nodes that are potentially able to relay that message. And if we treat this as a problem of shortest path routing, these numbers here represent the ETX values. So the shortest path from node I to the final destination in this case might be the first one. So you send your packet to this node, it sends the packet to the destination. So that incurs the total ETX in this case of 7. Okay. However, because it's a broadcast medium, when node I sends a message, even if J hears it, or regardless of whether it's or not J, this first node hears it, there's a probability that the second node may also hear it. Right? In fact, there's also a probability that the third node might hear it. And so the question is, if by some chance both these nodes hear the packet, who should forward it? In fact, it looks like it doesn't matter. But if for some reason this node didn't hear it when you sent the message and this node heard it, then instead of insisting that no, the route actually must go through that first node, what if you were flexible and allowed this node to forward the packet, the second node over here? Then for the same cost that the first one would have taken to forward the packet, this one could also forward the packet. But what you've saved on is having to retransmit the message back to the first node. Right? So that's the basic idea of any path routing, is that any of the following paths is okay. Either the packet traverses this route or it traverses this route. And instead of deciding which of those two routes you must take, what he says, we'll leave the decision up to after they get the packet, whoever has the packet can figure out to forward it or not. Now there is an implementation detail here which we'll get at, which is how should they coordinate with each other who should forward. So the simplest mechanism you can think of is maybe we ask both of them to forward, but then we're going to result in duplicate packets. They might even interfere with each other. Or intuitively, if the first node got the packet and whether the second one gets it or not, really the first one should be the one to send it. So we want to kind of prioritize our receivers. So we want to say of all the receivers that got the packet, the one who has the highest priority should transmit. And if for some reason that one cannot, then the second priority node should transmit and so on. So we have some notion of prioritizing from this set of neighbors. But once we have such a priority in place and we have a way of ensuring that, let's set aside how to do that for a second. Then let's think about what is the expected ETX now for this particular system. So if I can have the document camera again, please. So we're going to consider two alternatives. So alternative one is just using the top route, and we said that that is our single path, right, min-ETX solution, and it incurs a total ETX of 7. Now we're saying we have a different solution which looks as follows. Okay, we're going to call this the any path solution. In fact, there was a third node here. I'm going to leave it out for our discussion at the moment. And what would be its ETX? And also, what is the scheme exactly? So what the scheme says is, let me label these nodes. Let's call this the source node, the destination node. Let's call this node A and node B. And in this example, they labeled these ETX values as follows. For now, we're just going to make a simplifying assumption, just for our calculation purposes, that the ETX equals 1 over the probability of reception, or PRR. Okay. Remember that this is a good approximation if your system is basically IID and your acts are 100% likely to get back. So if I send a packet, on average it takes me 4 transmissions to get there. The probability that each packet will get through if it's an IID system is 1/4. That's what it's saying. So therefore, PRR for S to A would be 1/4. PRR for S to B link would be 1/5. PRR, and so these PRRs are also now sort of the probability of success, right? So the probability of success from A to D, that's 1/3. Probability of success from, although we don't need these numbers, but for completeness. So now, what is the algorithm going to do? It's going to send a packet from S. It's going to be a broadcast packet. Both of these nodes are potentially receivers of that packet. One of four things will happen. Either both don't get it, or B gets it and A doesn't get it, or A gets it and B doesn't get it, or they both get it. Right? And what the scheme will do is, if of course both of them don't get it, then the sender will get no ACKs back. It will retransmit the packet. Okay? So if neither A or B get it, no ACK, then you do retransmission. So you try again, and again one of these four cases will happen. If A gets it and B does not get it, then it will go ahead and forward that ACK back to S that it got it, and it will forward the message. Okay? So in this case, A will forward. If they both get it, or actually before I go there, if B gets it and A doesn't get it, then B is going to forward the message. And it will ACK back to S that I forwarded the message, so S won't have to retransmit again. And A won't do anything, it didn't get the message, it's not going to forward. B is going to forward it, and then D will potentially get it, or it's going to have, it's going to continue to forward from that point on. If, on the other hand, so if only A or only B get it, only they forward. Now, if A and B both receive, now we have potentially an issue, because if they both receive and they both transmit, they might interfere, or it's unclear, can you improve the efficiency somehow? So in this case, there's going to be a priority, and for now we're going to assume the priority is that A has higher priority than B. And so if they both get it, A will transmit and B will not. And we're going to suspend our judgment for a second about how we can guarantee that. So in this case, only A forwards. So A will forward in this case, and then the process will continue. In any one of these three cases, which is to say either B gets it, or A gets it, or A and B both get it, what will end up happening is one of them, either A or B, will start to forward, and from that point on, we don't really have a benefit to be derived from the broadcast advantage. They're not going to talk to somebody else, they're just going to talk directly to the destination. And if this ETX is 3, then on average it'll take them 3 transmissions to get their packet on to D. So that's where the second part of it in this example is very simple. So whoever forwards it, it'll take an additional ETX to get there. So now the question is, what benefit have we derived? The benefit we've got in this scheme versus this scheme is that here the only way for you to get the packet to be forwarded on to D is for A to get it. Now, if either A or B or both get it, it's going to be forwarded. So the probability of losing the packet in that first time step is equal to the probability that neither A nor B get it. Whereas in the first scheme, the probability of losing the packet in the first step is that A doesn't get it. So that's the reliability advantage, the diversity advantage we're going to exploit. So in this scheme, the probability of success at the first hop, okay, equals the probability that either A or B or both get the packet. And that's equal to 1 minus the probability that neither gets it. And if these are independent events, we're going to assume that they are independent. So if independent, it's equal to 1 minus, say 1 minus the probability of the packet getting from S to A times 1 minus the probability of the packet getting from S to B. And we said that the probability of S to A is 1 over 4. The probability of S to B is 1 over 5. So we put those numbers in. So we would get this is 1 minus 1 over 4. This is 1 minus 1 over 5. So 1 minus 3/4 times 4/5, which is equal to 1 minus 3/5, which is 2/5. So 40% chance of success in that first try. This is different from this scheme in which the success is 25%. So it's gone from 25% to 40%. That's the improvement we got in this example. And so therefore the ETX now, the total ETX of the AnyPath scheme equals 1 over the probability of success for the first stage plus the ETX for the second stage. In this example, the ETX for the second stage is 3. Doesn't matter who's going to forward it. For the first stage, it's going to be 1 over this probability of success because you're going to keep transmitting until this event happens. Right? So it becomes 5 over 2 plus 3, which is 5.5. And the ETX for the single path solution was 7. So the ETX for the second solution is better, and that's the benefit of the diversity scheme that we've introduced into the routing protocol. And so by allowing the reception and forwarding process to be a little bit more flexible, allowing a set of nodes to potentially receive the packet and forward it, you can potentially reduce the ETX value. So now there could be a little bit of a question still in our mind because I set it aside. So how to coordinate nodes A and B, right? So in particular, when both receive the packet, how to ensure that only A forwards the packet. And why is this a non-trivial consideration? It's because by definition, these are two different nodes. They're not being controlled by the same processor. And no centralized entity is aware of what happened. So if B receives a packet, it doesn't know whether A got it or not. If you write in your code, you get a packet, you forward it, then it'll forward it regardless of whether A got it. Right? So a purely distributed approach couldn't solve this issue. Right? Sort of a naive implementation would make B forward all the time, regardless of whether A gets the message. So from a protocol perspective or a distributed systems perspective, in order to implement this coordination, somehow B has to become aware that A got the packet. Right? So that's the problem that the protocol has to solve, because if you can't solve that easily, or if you have to introduce a lot of overhead to solve that, that additional overhead might kill the advantage you're getting out of the ETX improvement. So this is a good one to think about a little bit. So really, like a naive solution would just be when A gets it, A sends a message to B saying, I got it, you don't worry about it, I'll take care of it. Right? It's like, that's not a good example, but I'm just thinking like you're playing volleyball, there's two of you rushing to the ball, one of them says, no, I got it, I'll take care of it, and then you know not to go there. That's a coordination mechanism. But if we send an additional message just between A and B, that's like one extra message we have to account for. And even if the total ETX, total number of transmissions is 5.5, now you have like one extra message to also add into that, right? And that's going to reduce some of your advantage. So you want to try and reduce the additional signaling that might be required. So what are possible ways in which one can do this? And there's a couple of approaches. There's one approach, actually, really both of those are essentially the same idea, so maybe I just put them together. The key idea is to have separate timers or latencies associated with each forwarder as a function of their priority. So first of all, it's clear that node A, so if I'm going to potentially try to forward, what I want to do is I want to give priority to A. And so we're going to have A on a fast timer. As soon as it gets the packet, it should try and forward. Okay. The idea of giving it a faster timer is that B will get some time to figure out should it forward or not. And hopefully we'll learn whether A has forwarded or not. And so this timer can do one of two things, can do both things, which is that as soon as A gets the message, it sends an ACK back. That ACK is typically also a broadcast message. Right? So whatever you're responding back is, it's a wireless medium. If you're not a directional radio, it can be heard by everybody nearby. So it allows for the possibility that B will actually not hear a message specifically intended for it, but will hear A's acknowledgement of the reception of that packet. Right? And that will signal to B that A has it. So that's one way in which we could address it. It's just, before you jump off and start doing anything, you wait and see if A got it. And then B might have its own timer for the ACK, which will wait for a while and then send its acknowledgement. So its acknowledgement doesn't get sent at the same time, maybe to avoid collisions, for example, of the ACKs, because multiple receivers receiving it, all of them ACKing would be a bad idea. The second thing it can do is A can go ahead and forward sooner than B if it got the message. B has a timer that hasn't quite expired yet. It hasn't started to even send that message. And before it even does that, A could forward the message on. And in this case, also, B has the possibility of overhearing that the packet was forwarded, and maybe now I don't have to do it. Somebody else who has higher priority has taken care of it. So long as I can make sure that whoever has higher priority has lower latency, and I can hear them either when they respond with an ACK or when they forward the packet, then I'm okay. So this is typically the way we use to resolve the contention and resolve this coordination issue. Is basically set them on different timers. A kind of does everything much quicker, B is a little bit slower. If there was a third member of the forwarding set with even lower priority, it would be even slower than B, and so on. But this does require, for a successful implementation, that B fairly reliably hear either the ACK or the forwarded packets of A. In fact, hearing the ACK packets of A is generally more easy to ensure reliability about, because ACK packets, as I mentioned before, are small packets, tend to be much less error prone, tend to actually have a larger range that they can be heard than data packets. So if you stop and think about that for a minute, it's a non-intuitive idea, which is that in a wireless device, the smaller your packet, the farther out you can be heard. Okay, and the simple reason for that is that the probability of errors is the same in each case per bit. The fewer the number of bits, the chance that a small number of them get knocked out is lower for the smaller size packet. And so that's one way to improve the performance. And finally, what's the absolute worst case is that they both do transmit. For some reason, the signaling gets messed up once in a while, and they both forward the packet. So probabilistically, you might have a higher overhead. But even in that case, whoever they're forwarding to, if it happens to be a common node, its acknowledgements will suppress further transmissions from the other node. So if both of them, basically do forward and A forwards sooner, D might act back to that, and depending on what these timers are, either B is already forwarded or it hears, might even hear this ACK and decide not to continue to forward. So some additional logic at B that listens to these packets, either acknowledgements from A or forwarding from A or ACKs from D, all of these can help suppress further forwarding from B. And even if absolutely even beyond that, B goes ahead and sends the message, D hearing the same message coming twice simply makes sure it only forwards them once. It doesn't send multiple copies of the packet to flood the whole network. So that's duplicate suppression. So by a combination of these various schemes, you can kind of reduce the overhead associated with the AnyPath solution, and people in practice have tried to implement AnyPath solution and have indeed found improvements in ETX, in the latency, in the energy cost, in the throughput, and all of the different metrics we talked about last time. So this illustration of any path, however, doesn't tell us what the routing protocol should look like. For single path minimum ETX routing, you know what the routing protocol should look like. You run Dijkstra or Bellman for. So what this paper by Raphael Laufer does is it basically generalizes Dijkstra's algorithm to any path routing. So how does it do that? If we can switch back to the projector, please. So in this paper that calculation is described as an algorithm here. So in the paper it's referred to as the shortest any path first algorithm. It's meant to be a reference to how in traditional shortest path routing, we talk about OSPF is like open shortest path first. So this is shortest any path first. So before we walk through this algorithm, there's a couple of steps that we want to get at, or okay, let me get the high level idea, then I want to go back to a couple of calculations we will need for this algorithm. So the basic idea is you're given a graph, and what the algorithm is going to do is going to compute the shortest any path from all nodes to a given destination D. This is kind of what your Dijkstra's algorithm does. You have a final node, and you say what is the shortest path to this node from different sources. And just like Dijkstra's algorithm, but somewhat different in the implementation details, it's going to try and iterate and improve an estimate for the shortest path, in this case any path from each one of those nodes to the destination, and iteratively improve them to the point that you get the final solution. And you keep for each node something called a forwarding set. And that forwarding set is like the example we just saw. It's like when you send, who are the receivers who you want to try and forward your message, and what's the priority order in which you want them to try and forward your message. And it requires a couple of data structures called S and Q, and we'll come back to this. Basically, S is all of the nodes for which we've already figured out the shortest any path, and Q is the other node from which we keep pulling and putting into S, and when Q becomes empty, then you're kind of done. So before we look at the details of that, let's describe the metric that's being used here. So first of all, there is the notion of computing something called the PI capital J, which is going to be let's look at this one, yeah. So, yeah, if I can switch back to the overhead camera. So if you have some node I and some node J that's going to be your final destination, you're interested ultimately in actually, maybe I shouldn't call this J. Okay, so let's leave this out. So we're interested in kind of characterizing the distance from node I to the final destination. So this is the destination node. Traditionally, the way you would have broken your calculation is if this was some node J in between, you would say your total cost, for going from this destination from this node to the destination, let's call that capital DI, is equal to some local cost from going from I to J plus the cost of going from node J, right? So this is like your building block of the iterative calculation, the recursive calculation that fundamentally shows up in both Dijkstra and Bellman-Ford, in fact. But it's sort of breaking down your, this path might actually take more hops than even this, right? You might be going through the rest of the network to get there, but if you knew the cost of, from this node, how to get the packet to the destination, and that was dj, then the cost to get the packet from I to j is basically, if we were to take this particular route, would be the distance to get to that node j plus, the remaining distance. The difference now is that instead of just having one node, we're going to have a set of possible forwarders. And in the example we looked at, it was 2, but it could be, multiple nodes in between. And we're going to call that set, so instead of a forwarding neighbor, we're going to have a set. Now we're calling it the forwarding set. Okay, let's call that capital J. Then di is going to become the distance of going from I to the forwarding set plus the distance from the forwarding set onwards. Okay, so here it was like the local cost, and this is sometimes called the cost to go. And so this part is the local cost, but to a forwarding set. And so here was local cost to neighbor, and forwarding cost to, cost to go from neighbor, j. Here it's a local cost to the forwarding set, j, and this is the cost to go from set j, right? So we're basically going to have to redo this calculation. In fact, we just did that for that special example. So that local cost, we said, is basically a question of the probabilities of reception by each node in the forwarding set. Okay, so if, for example, your forwarding set has n nodes in it, so let's just call them 1, 2, up to n. They are associated with success probabilities pi1, pi2, ... pin. And for simplicity, since we're fixing in this example the node I that's going to send it, I'm just going to simplify this notation, just say p1, p2, up to pn. So again, just to clarify that picture, we're saying there's a bunch of these nodes, 1 up to some n. And for each one of them, right, if this is some node j, there's a pj, p1, pn, and so on, right, associated with the forward success probability. So this cost will depend on those forward probabilities. And we're going to define Pij as the success probability to get packet at least one node in J. And we're making an assumption that the d, sorry, what did we call it? Small d. Small dij is 1 over pij. Okay, so this is assuming IID success. So if I can compute 1 over, if I can compute Pij, Dij is just 1 over that number. What is Pij? It's the probability that at least one of them gets it, which is 1 minus the probability that none of them get it. And we just did that calculation. So Pij is 1 minus the product of all of the others not getting, of all of them not getting it. So all of the nodes j going from 1 to n. Right, so this is the probability that at least one of them gets it is 1 minus the probability that none of them get it. Okay. So this product, by the way, implies that we're also assuming independent link success. And in this paper, as well as for our calculation purposes, we make these assumptions about IID transmissions and independent link success. It turns out in practice, neither is your transmission probability IID, nor is it true that your links are independent of each other in terms of their success probability. So in practice, you need a more robust way of calculating the Dij metric. And the simplest way you can just calculate it in practice is not to make these assumptions, but just physically compute. Like we were doing an ETX estimate, there was the ETX estimate from node I to node J. Here you would have to compute an ETX estimate from a node I to the set, right? So implementation details are going to be a little bit more complicated than the simple math derivation here, but let's stick with this for now and bear in mind that in practice, some of the assumptions behind the derivation are not going to hold 100%. So if I know this probability, then I can compute Dij is just 1 over that. So Dij is simply, right, 1 over 1 minus probability J goes to 1 minus Pj. So this is fine. What about the cost going forward from each of these nodes to the final destination? So in the example we worked out, this was kind of simplified by the fact that it didn't matter who got it, they all had cost 3. But in general, that may not be true. Some of them may have cost 3, some of them may have cost 4, some of them may have cost 7, and I want to take all of that into account in making my decision. So Dj is the cost to go from set J to destination. So let's think about this for a second. So what really affects it? So if I focus on each of these nodes over here, they may each have a different cost going forward. So if I actually look at the other side of that, right? So this side, it just says P1, Pj, Pn. But in the other side of it, they may have like different costs associated with them. D1, some cost D2 here, some cost Dn over here. And so depending on who forwards it, I may end up with a different cost to finally, get through the network to my final destination. So can I compute, if I know that all of these nodes are in my forwarding set, how do I compute my expected cost? And that's the key idea here, is it's an expected cost to go from set J to destination. So this is a random process. So with some probability, node 1 gets it, and it will be the forwarder. And with that probability, my cost to go will be D1. With some probability, this node doesn't get it, and the second node in my system, and this is J, but the second node in my system might get it, right? In which case, that will be the forwarder, and its corresponding cost to go will be my cost to go. So the point is that if I can say, what's the probability that each node is the forwarder, if it gets the packet, and multiply that probability with the cost to go from that node, that's my expected cost to go. So in other words, Dj is the summation of j going from 1 to n of some wj, which is going to be the probability that that node is the forwarder, times the cost to go from that node onwards. So this is the probability that node j is the forwarder. Right. So how do we compute the probability that a given node is the forwarder? So we can take a quick example. So we had that 1/4, 1/5 type of an example of the probabilities of success. Let's, instead of 1/3, 1/3, let's just change this number to be different for the two of them. So let's say this was 1/3 and this was 1/4. And, say this was our setup. What's the probability that node A is the forwarder, and what's the probability that node B is the forwarder? Well, the probability A is the forwarder, okay, is the probability that A gets it divided by the probability that A or B get it. Why is it divided by? It's, let's simplify this a little further. So we want to define two events, and we'll see that basically this is a conditional probability, and this term at the bottom is basically accounting for the conditioning. So what's a good way to see it? So it's if you remember from probability, if you have like some x given y, it's the probability of x and y divided by the probability of y. So what we're saying is that the probability that A is the forwarder, okay, equals the probability that A got it, conditioned on the probability that A or B, right, or both got it. Why is this conditioning needed? Is because if none of them got it, and you just focus on the probability that A got it, it sort of doesn't account for the case when basically neither of them gets it, in which case it's not that B becomes the forwarder, it's that you retry again. So you want to kind of focus yourself in that portion of space where definitely somebody is going to be the forwarder. Of all the times that somebody is the forwarder, what fraction of times did A actually forward that packet? Okay. If you don't do this conditioning, if you just did what's the probability A got it, what you'll end up doing is you will try to say that the probabilities of A being a forwarder plus the probability of B being a forwarder should add up to 1, but they won't add up to 1 because that will just be 1/4 plus 1/5, right? They don't even add up to 1. So we want to focus of conditioning on the fact that somebody got it, somebody's going to be the forwarder, what's the probability that A is the one that's doing it? That's what we're interested in. So that's why we have this conditioning. And so this is equal to the probability that A gets it and A or B or both got it divided by the probability that A or B or both got it. Right? But what's the intersection of these two events? A or B or both get it, A gets it, the intersection of these two is just A gets it, because A gets it is already contained within this larger event. Right? So that's the probability that A gets it divided by the probability that A or B or both. Okay? So that's what we're using as our weight WA here. So this WA, if we know the probabilities involved, could be written very generally as follows. So WJ in general would be written as the probability that node J gets it, and nobody who is higher than it gets it. So if you're talking about node B, for example, it would be the probability that B got it times the probability A did not get divided by the probability that A or B got it. Okay? The division is for the same reason, but in the numerator now, B is only a forwarder if B gets it and A does not get it. Okay, so in this case, we also have to also account for the fact that A did not get it, because B will not be allowed to forward if A is forwarding. So this is the probability that that particular node gets the packet, and nobody with a priority value that's less than this one, from 1 to J minus 1, gets it. Divided by the probability that at least one of them gets it, which is 1 minus the product of J goes from 1 to N of 1 minus P J. So here's a general expression for probability that node J in the set J, which is just 1 to N, is the forwarder of a packet from node I. Okay? Given probability of success from I to j equals pj. So if that's how we define our success probabilities, we're given a set with this priority ordering where this is the highest priority, that's the lowest priority. This general expression tells us what's the probability that the jth node in your forwarding set will be the forwarder. So putting it all together, we get, we started with this one, and we broke it up into two pieces. We said this is 1 over Pij. Okay, and with j is for the full set, which is this, and so Dij, the first term is this. And then we said the second term over here, D capital J, is an expectation which can be computed as this. And now we've calculated W sub j as well. So the capital D J's were given to us. All of the P1, P2 are given to us. And given all of those, we can then compute our final answer as follows. So Di equals Dij plus Dj, which is equal to 1 over Pij plus summation Wj dj. This is 1 over 1 minus the product of 1 minus Pj. This is the summation of this expression we have on top here. Pj product k goes from 1 to j minus 1, 1 minus pk over 1 minus. Okay. So what does this allow you to do? This equation given a forwarding set J and all of the DJs for all J and J, and the success probabilities Pij equal to Pj, that's how the notation we used for all J and J, computes Di. Right? Just as in the original standard single path routing, if you know the distance from a node to the destination, you know your distance to that node, you just add up those two numbers and that gives you the distance to the destination. It's the exact same idea, it's just we have to generalize it with all of these probabilities because we're exploiting diversity. And we have a particular protocol in place. Okay. So it's a lot to take in, but really at the end of the day, we're just coming up with a calculation to help us figure out what is my distance to the destination in terms of any path ETX, given that I know the distances for all of the nodes in my forwarding set and I've chosen a forwarding set. So that basically leaves open only one question, which is how do I compute the forwarding set for each node? And so that's what the algorithm that's presented in that paper does. So here is the algorithm itself. Let me write it down here and we can basically try and make sense of it. So this algorithm that goes by the name of shortest any path first algorithm takes as input to the algorithm the graph describing the network as well as the link costs associated with each link in that network and the probabilities which you can derive from the distances, as well as this is the destination node. Okay. So it goes for each node I in the vertex set where G equals some set of vertices and edges. So for each node in V, the initialization is you set initially the distance to be infinity, and you initialize the forwarding set for each node initially to be the empty set. So this is basically the initialization. Then for the destination node, the distance is 0 because it is the destination node. there's going to be two sets that we maintain called S and Q. S initially is empty, and Q initially has all the vertices of the whole graph in it. And as the algorithm proceeds, we keep moving nodes from Q to S. When eventually Q runs out and S has all the nodes, the algorithm is going to terminate. So the while loop in the algorithm basically just monitors this Q, and so long as it's not empty, so make sure my notation is sufficiently clear. So here, by phi, we mean the empty set. Okay. So this set Q, so long as it's not empty, we're going to run a routine called extract min. From Q. So what does extract min do? Is it's going to pull out the node with the smallest distance to the destination. So this basically pulls out vertex with smallest di. So when you first start the program, this algorithm, all of the nodes have distance infinity except the final destination. So the first node to get pulled out from Q through this extract min operation will be just the destination node. That will be the very first one. Then we're going to add to set S this new node. So that simply updates S to take this extracted node into it. And this is the key step actually for I should have been a little more careful maybe. No, this is okay. So for each incoming edge, I comma j, where j is now referring to this node that you just pulled out. I is referring to every node that has an edge pointing to this node that you just pulled out. Okay? In the set of all edges, what we're going to do is in the forwarding set for each of those nodes, we're going to add j at the bottom. So maybe currently their forwarding set is empty, you will add j to the top, or if they already have a forwarding set, this node j is going to go to the bottom of that set. And you're going to do one step of comparison, which is, are we going to take this new set and make it part of our new forwarding set for I or not? And to do that, we do one comparison, which is if di is bigger than dj, so you check whether when you add this node j, there's going to be some distance that you can, go from j to the destination. There's a distance you already have for going from I to the destination. If this condition is not met, in other words, if di is actually less than dj, there's no hope that adding j as a forwarding node will ever help you. Because the only reason for you to forward to somebody is that if they can get the data quicker than you can. Right? And so this is telling you that first you check if di is actually bigger than dj. So if this is true and only then, we're going to calculate di from dj and the other values that we have as the equation that we just talked about. Okay, so this calculation is the one we just talked about. How do you do this calculation? So dij, how do you compute it? We said is this expression, and capital DJ, that's this expression. Right? So this computation step is right here in the algorithm. And then finally, if this condition holds, once you've updated the distance, we can actually add j to the forwarding set, or make j the forwarding set for I. And it just loops back and repeats. So basically, this loop is the one that's the main code. It keeps running. And at every iteration of this loop, it pulls whichever node has the shortest distance to the final destination at present. And then for every, so it makes that node part of the set of nodes for which we've settled the forwarding set. We're not going to compute anything more about this node. And then for everybody that has an edge to this node, we check and see, would it make sense to make j a member of the forwarding set of those incoming neighbors, of those nodes from which it has an edge. And if it makes sense, which is this condition, then we update the calculation for DI. So this calculation will basically reduce, you can prove that by this calculation we will actually reduce DI. Since this condition holds, DJ is actually smaller. By adding an additional term which is smaller than your original value, you'll actually reduce DI. And so in this case, it would actually make sense to treat it as a forwarding neighbor. We will update the distances for I to take into account this node and make J part of the forwarding set for I, and then continue. So you'll get a chance to, this is one of those things you just need to sit with a little bit and kind of work through an example. Let me kind of show you the illustration that's in the paper and walk through it a little bit. The paper doesn't actually work out all the calculations, and that might be something you might want to do to kind of convince yourself of how this works. So let's look at the screen again, please. So here's the execution of the shortest any path first algorithm. We're starting with a graph G, and it has a set of vertices, it has a set of edges. All of the edges are labeled with distances. The assumption here is that the probability of success is just 1 over the distance, because the distance is 1 over the probability of success. And this node on the far right here is designated the destination node. So when we first start the algorithm, all of the nodes are initialized to a distance of infinity except the destination node. So extract min will pull out this node first. Then there is a part of the code that did like for each incoming edge ij in the set, we're going to check something. So these are the incoming edges. So basically nodes 2, 4, and these are not labeled, but this node, and this node each have the destination as their at the other end of an outgoing edge. And so these are the 3 nodes we're going to consider in turn. Let's start with the first node. We're going to check initially, if we added D to their forwarding set, initially their forwarding set is empty, we're going to add the destination to their forwarding set. Is the distance with the, so from the distance of the destination is 0, their distance initially was infinity, which is clearly smaller. So it will pass that if Di greater than Dj check, because infinity is bigger than 0. And then we're going to update their distances to be the distance of getting to here plus whatever additional forwarding cost there might be. So in this case, the cost to go 0, the forwarding set only has one element now, just this node, and so that's going to get updated to be their cost to get to the destination is just the distance directly to get there. So this one will have a cost of 2, this one will have a cost of 4, this one will have a cost of 7. So after that first run through it, this node has been pulled into the set Q, and these 3 nodes have their distance values updated, their forwarding set updated to include the destination directly. So any one of these nodes will make sure to put the destination as their preferred forwarder, which is to say, if the destination gets it, we're done. Right? So a special case of a forwarder is that you got the data, you don't have to do anything with it. So now we go on to the second step. So in the second step, of all of the nodes that are in your graph that are not in the set S, but are actually in the set Q. So once we pulled out the destination, this node is no longer part of the set Q. The extract min operator looks at all of these numbers, infinity, infinity, 4, 7, 2, picks the minimum of those, which is this node, having a cost of 2. So now this node will be put into the set S, right? And so that's kind of shown here. And you will start to consider its incoming neighbors, which are this node and this node. You will ask for each of them. So this one had a cost of infinity. You have a cost of 2, which definitely is lower. So this node will be added to the forwarding set of 7. And the total cost for this node will be updated to the forwarding cost to get to this forwarding set, which at the moment is just 2. So it's just distance that was labeled as 5, plus the cost to go from 2, which is 2. So 5 plus 2 is 7. That becomes the new updated cost for this incoming neighbor. And its forwarding set is updated now to make 2 its forwarder. This node, which also had an edge to our the node we've just entered, has an interesting story, because if you look back here, the cost for this node to get to the destination is 2. The cost for this node to get to the destination was 4. It had been updated, but it's 4. It already had the destination as a forwarding set node, but now it's going to, because that condition is met, 4 is bigger than 2, it's going to add 2 as one of its forwarding neighbors. So the forwarding set for this node over here at this point consists of the destination as the first priority, and this node is the second priority. So when it sends a packet, if the destination gets it, it's done. If the destination doesn't get it and this node gets it, then it would have basically the command of, or the control over forwarding the packet from this time on.
Excuse me, Professor, is your 5-minute warning?
Thank you. And you can see now why we did that test, which is that now that you're successful, you would rather have this node try to forward, because its expected cost to get to the destination is 2, whereas if you didn't include it as a forwarder, your expected cost to get to the destination was 4. So instead of retrying the packet yourself, you might as well hand over control to this node to do it. Right? And so that's why this node gets pulled into the forwarding set for this node. You do the calculation we just talked about, and if you do that calculation, you find that its distance is going to go down from 4 to 2.5. Okay? So now we have these two nodes already added to S, and Q just consists of these 5 nodes, and the smallest of them is this node. So this node becomes the node that gets added to Q, and then you look at all of the incoming neighbors, which is this node and this node. Because their distances are bigger than 2.5, they will get updated and include this node in their forwarding set. Now you will look at the remaining nodes over here, have cost 5.2, 6.5, and 7. The smallest of those is this node, so that node becomes added to the set S. And now you compute for this node, which has a forwarding edge into it, whether it should be updated, and it should, because it started with an infinity, so it gets updated to point at this node as a forwarding neighbor. Now we just have these 3 nodes to pick the minimum from, which happens to be this node over here, 6.2. It actually has nobody pointing at it, so therefore nobody else gets updated in this round. That leaves only these 2 nodes, 6.5 and 7, are their current distance to the destination. So this node gets pulled in next. It also has no existing node that is not already kind of solidified, if you will. Everything that moves into S cannot be changed again. So it also does not require any additional updates. And then finally, you're left with node 7, and that also requires no further updates. So this is your final configuration, in which along the way, we basically updated the forwarding set for this node over here, for example, to include both this and this. We updated the forwarding set for this node to include these 2. But if you look at this node, it only has 1 neighbor in its forwarding set. This node only has 1 neighbor in its forwarding set. This node has only 1 neighbor in its forwarding set. These 2 nodes only have 1 neighbor in their forwarding set. Okay. So some of the nodes got a forwarding set of more than 1 node. This turns out, and you can prove, we don't get into the proof of it, to be the best possible configuration in terms of an anypath routing mechanism. And the final numbers labeled at every node is the shortest anypath cost for those nodes. We're running low on time, but we can do a quick test to see if this is better than just single path routing. And a good example would be to look at this node over here. So this node over here, if you'd done shortest path routing, you could have gotten the data from it to the destination for, I think the cheapest you could do it is 5 plus 2, 7, right? But with anypath routing, we're able to reduce its cost to get the data to the destination to 5.2. So you can see the reduction in ETX obtained by doing anypath routing. So that's sort of the full story about anypath routing. So it takes a little bit of time to digest. We will put up this paper and the other paper I mentioned on our DEN site. I highly recommend reading through it carefully. The paper has some additional stuff about multiple rates. You can ignore that. I think all we care about in this class is this standard single rate case where all of the links have a fixed data rate associated with them. Okay, so we'll stop here.
This concludes EE 597 with Professor Krishnamachari on Wednesday, July 20th, 2016.